code for the class is going to be 7538. I'm going to say it again. Today's code for the class is going to be 7538. So far, we've seen a general picture of how reactions are written in organic chemistry, and we've explored how the general reaction goes. But what we're going to see in this chapter is the detailed description of what bonds are being broken and what bonds are being formed, and that is what we call the reaction mechanisms. So I want you to understand the difference between showing the overall reaction like we did in the Grignard reaction before. Remember, we had CH3MgBr. Remember, there was a 1, 2, water. And then, so here we had that the result was this, right? So this is the overall reaction that's happening. But the detailed mechanism is where when we start showing what electrons are moving, what bonds are formed, what bonds are being broken. And so I showed you the mechanism in an earlier video, so I'm not going to repeat it again, but that's the overall mechanism. So that reaction can happen in either one step or it can happen in a bunch of steps, right? And so we'll see many examples from now on. So when the reaction just happens in one step, that reaction is what we call a conserved reaction. So for example, we have here, I don't know, I have Br, right? So these bond right here can break. So I have, because the Br is pulling electrons, and then here I have Cn minus. And you know, Cn minus, it's a nucleophile, right? It has the negative charge, it has the electrons. And so my electrophilic side will be that carbon right there because it has the delta plus, sorry. Remember that the Br will have the delta minus and that carbon will have the delta plus. So that Cn can come and kick the Br out. And so the result is this plus the Br. Right? So this is a concerted reaction because it happened in just one step. And then the opposite is a stepwise reaction in which the reaction happens in a bunch of steps. So for example, if I have something like this plus the Cn minus, what will happen is overall I'll have the Cn come in, but this reaction will go through an intermediate, and that intermediate will be that carbocation forming, and then at that point the Cn can come and attack, and then I'll get the product. So it's okay if you didn't follow the reaction, that's totally fine. These are two substitution reactions, but what I want you to understand is that one reaction can either happen here, that can happen just in one step, or it can happen stepwise if we go through an intermediate, right? Okay, so that the bonds that will break, they can break in two different ways. So the bond breaking can be homolytic, which means that each part of the molecule will get exactly the same. So remember that when we have one bond like this one, we have one electron and two electrons. When the homolysis happens, one of the electrons goes to the A and the other electron goes to the B. Because not two electrons, not two full electrons move like we are used to see, we will draw this half hooked arrow, right? So it's not a full arrow like that. That's not how we will draw it. We'll draw like this, right? So it's half of a hook. It's just one side. And so in this process, we generate two species. There are no pluses or minus, but the A has an electron and the B has an electron. This species is what we call a radical right here. And those radicals are very, very unstable because they contain just one atom. So as you can imagine, they are looking for the other atom. They only contain one electron. So as you can imagine, they are only looking for another electron so they can fulfill the octet. The other option is that we have a heterolytic bond breakage, and that's what we have seen before. So remember when we had an acid and a base, and the base will go and pick up the hydrogen from the acid, right? And so you see here there is an electron, well, two electrons, right? And so we would say that the acid gets both of those electrons because hydrogen can only form one bond at a time, so it will form it with the base, and then the acid will get those two electrons. So that's exactly what we're talking about here. So this is a heterolytic bond cleavage, and so you have two options. In this case, either one part of the molecule, B, gets the electrons, or the other part of the molecule gets the electrons. Remember that the electrons will go to the more electronegative atom, right? That makes sense because it's the one that can pull the electrons more strongly. So in the case of heterolytic bond breakage, you will draw the full arrow, right? So for homolytic, we'll do 1 and 2. And so for heterolytic, we'll do like the full arrow. So when heterolytic bond breakage happens, what you get is either a carbocation or a carbanion. So you've seen this before. A carbocation has a plus sign and the carbanion has a minus sign, right? So you are familiar with this. So here is one example of each one of them. So this one is the homolytic bond breakage, and in which one of the electrons goes to that carbon, the other electron goes to the other to the Z. And so this radical is extremely unstable and it's looking for electrons. And then here we have the two types of heterolytic bond breakage. One is where the Z is more electronegative than the carbon, and then at that point the Z will take the electrons and the carbocation will end up with a plus sign. In the other side, you have the Z being less electronegative than the carbon, and then the carbon is the one that takes those electrons, and that's why we end up with a carbanion that has 5 electrons around itself, and that's why we have that negative sign. So these are the 3 species. So they are all very reactive at this point. They will always be intermediates. We cannot, so when we're in the lab, we cannot isolate these species because they will react with absolutely everything. So electrophiles will be, so sorry, both the radicals and the carbocations will be electrophiles, so they will receive electrons. So here, these two. So a nucleophile will come and attack there, or will come and attack there, and the carbanion will act as a nucleophile right there. So these act as electrophiles, and this carbanion acts as a nucleophile, right? Because it has this excess of electrons, and that makes it ready to go and attack an electrophile. Right? So in other words, you have a plus here that will receive the electrons, that will accept the electrons, and here the carbanion will go and attack to get, because this is the electron rich. So how do bonds form? So we have 2 options. So when we have 2 radicals, the same way that they separated, they will come together. So you see it's the opposite. So in here, one went to the A, one went to the B. So here you see that the opposite happens. So the A will bring one electron and the B will bring the other electron, and so that's how the bond will form in between. And in here, that's what you've seen more often. You have the A that has the plus the B that has the minus. What happens is they come together. The B shares a whole lone pair, right? And then at that point you can form the AB they will. So in both cases, the result is the same. You end up with a bond here and a bond here. The difference is where those electrons are coming from. In this case, your electrons are coming one from each side, and in this case, your electrons are coming one from, the A is not giving anything, everything is coming from the B. And so here it's just a summary and a reminder of how many types of arrows we use in organic chemistry. So this is the one that you may have seen more often up to this point, right? We have the reaction arrow. You've seen in general chemistry also the double reaction. That means that the reaction can go either forward or backwards, right? So we saw this quite a lot for in the acid-base chapter. Remember, the reaction could go either way. Then we also have the double-headed arrow. That, remember what that was for? That was for resonance structures, right? Remember, resonance structures are the ones where only electrons are moving around. And now here we have a full-headed arrow, and that's the one where two electrons are moving at the same time. And the half-headed arrow is the one, we call it fish hook because it looks like that, like a fish hook, and that's the one where only one electron is moving.